All right, today we're diving into a totally fascinating new way of thinking about artificial intelligence. It all comes down to one question. What if an AI didn't need mountains of data to get smart? What if, instead, it could just learn the fundamental laws of physics? Let's see how that actually works. I mean, just think about that for a second. Imagine an AI that doesn't just spot patterns, but actually starts to understand the why behind them. Things like the conservation of mass or how energy is supposed to flow. It sounds like something out of science fiction, but it's a real approach that's being used to solve one of AI's absolute biggest hurdles. So, first things first, let's set the stage with the main challenge here. Why do we even need a new approach? Well, it really all comes down to AI's enormous appetite for data. And this right here really shows the fundamental disconnect. The kind of AI we use every day for things like recognizing photos, it needs millions and millions of examples to learn from. But in so many critical scientific fields, like, say, modeling the airflow over a new airplane wing, getting that much data is practically impossible or just way too expensive. It leaves researchers stuck in what they call the small data regime. So this brings us to a really, really clever solution. If you don't have enough data to show the AI what's happening, why not just tell it the rules of the game from the start? And this is where the hero of our story comes in, the Physics-Informed Neural Network, or PIN for short. Think of it as a hybrid. It learns from the few data points you give it, sure, but it's also constrained by the laws of physics that govern the system, like the Navier-Stokes equations that tell you how fluids are supposed to move. The real key here is that its answers have to satisfy both conditions. So how does this actually work? Well, you can break it down into about 3 steps. First, you start with a pretty standard neural network. Then you feed it the very limited, sparse data that you actually have. But, and this is the magic ingredient, you add a brand new rule to the process. You tell the network, hey, whatever answer you come up with, it absolutely cannot violate this specific law of physics. To really get a handle on how that rule is enforced, let's use a simple analogy. Just imagine the AI as a student, and it's being trained by 2 different teachers at the very same time. This analogy makes the training process super clear. Teacher number 1 is the data. This teacher grades the AI on how well its predictions match the real-world measurements you have. We can call that error MSCU. Then you have teacher number 2, the physics. This teacher checks if the AI solution is actually following the governing equation. This error, MSCF, measures how much the AI's answer breaks that physical law. So the whole goal for the network is to make both teachers happy at the same time. It has to tweak its own internal connections to minimize both of those error scores, finding a solution that doesn't just fit the little data we have, but also makes perfect physical sense in all the huge gaps where we have no data at all. Okay, so that's the theory. Sounds pretty cool, right? But does it actually work in the real world? Let's check out a couple of seriously powerful examples from the research that show just what this thing can do. For the first challenge, the researchers asked a really tough question. Could a pin not only model a fluid's flow, but maybe even discover hidden properties of that flow that it was never ever shown? So the problem was modeling those complex swirls of fluid, those vortexes that form behind a cylinder. Now get this, they only gave the AI 1% of the velocity data. And here's the kicker, they gave it 0 data about the fluid's pressure. None. The AI had to figure out the entire pressure field all on its own, just by knowing the rules of fluid dynamics. And the result was just remarkable. The pin perfectly reconstructed the entire complex, swirling pressure field. It basically inferred a physical property it had absolutely no data for, simply because the laws of physics demanded that that pressure field had to exist in that exact way. And if you want the hard proof, here it is. The pin was also asked to identify key numbers inside the physics equation itself. This table shows the parameters it discovered for convection and viscosity are almost identical to the real correct values. So it didn't just solve the problem, it basically learned the underlying physics equation from scratch. Okay, if you thought that was cool, the second challenge pushed this concept even further. Could a pin predict a system's state far into the future, not by taking a million tiny little steps, but in one single giant computational leap? The system they used is described by the Allen-Kahn equation, which is often used to model how mixtures separate over time, kind of like oil and water. The challenge was to predict what the system would look like after a time step of 0.8. And for a complex system like this, trust me, That is a huge leap forward, one that would be incredibly difficult for traditional methods to do in a single go. So this is what the system looked like at the beginning, at time equals 0.1. As you can see, it's a smooth, pretty simple wave pattern. The AI was only given this single snapshot. And this is its prediction for what it would look like at time equals 0.9. It's a completely different, way more complex, and almost jagged pattern. And it's not just a wild guess. It is a stunningly accurate prediction of the final state. And it did it all in one computational step. Now, these examples, they're not just clever party tricks. They're really signaling the beginning of a whole new era for scientific computing and for discovery itself. So what's the big picture here? Well, this approach helps crack that small data problem that's held back AI in so many scientific fields. By embedding physical laws right into the network, it makes the AI less of a mysterious black box and more of a tool we can actually understand. And as we just saw, this can lead to discovering hidden phenomena and creates this amazing new synergy between machine learning and classic science. And this really leaves us with a fascinating final question. We've just seen how teaching an AI the rules of how fluids move or how materials change can unlock some incredible predictive power. So, what else is possible? What mysteries in climate science or materials discovery or even biology could we finally solve by combining our knowledge of the laws of physics with the raw power of AI?